guest today, Randy Blood. So Randy is a geologist and petrophysicist based in the greater Pittsburgh area, working on various aspects of Paleozoic strata in the Appalachian Basin. His current interests include evaluating sedimentary features within mudstones and how they affect hydrocarbon transport, drilling and completions, and the distribution and accumulation of critical minerals and rare earth elements. Before starting DRB Geological Consulting, he worked for EQT Production and Chesapeake Energy, evaluating their unconventional assets, defining horizontal landing zones, and using inorganic geochemistry data to model facies, estimate rock mechanics, and help solve wellbore stability issues. He also has experience evaluating unconventional assets and sedimentary successions in basins across the United States and abroad. And today he's going to be talking about creating giants, insights into the depositional and diagenetic pathways that created two of the most prolific unconventional reservoirs in the United States, the Ordovician Utica Shale, Point Pleasant Limestone, and the Devonian Marcellus Shale. And throughout the talk, please enter your questions you might have in the chat. And I'll do my best to facilitate at the end of Randy's discussion today. And he's more than happy to answer those questions. So we're very fortunate and happy to have Randy. And with that, I'll turn it over to him.
All right, well, thank you so much for that introduction. And let me get this set up here. And I can't do two things at once, so. All right, so hopefully you all can see that title screen there. And again, thank you so much for taking the time out of your day. I know it's precious, so to listen to me yammer on about two shale plays out east, I really appreciate it. I've always wanted to do a RMAG talk, and so to Ali Joffrey for helping set this up, and Debbie and the crew there for making this happen. So with that, I guess we'll get right into it here. The reason that I started looking at this in the first place was, and I think anybody who is in the industry, in sort of like the mid 2000s will remember this. I always said, there's the Barnett Shale, which was like the greatest of all shales, and that's why I jokingly have this graph over here off to the side of awesomeness. And the interesting thing was that there's always this idea that like the Barnett was the best. It was, it was the gold standard for shale plays. And there was this search for the next Barnett. That's what I really talked about. So there's always two shales. There's the Barnett and the next Barnett. But there's this idea that the next Barnett was never going to be as good as the Barnett Shale. And there was a lot of work, geology, science that had gone into understanding the Barnett, and obviously it had to. It was, the first shale play. We'd never tried to extract hydrocarbons from this group before, and this model was created. The problem that I ran into was there started to be this argument from a point of view, whereas we weren't looking at other shale plays, we were looking for other Barnett shales. So we had an answer, and we were looking for a question that fit that answer. So in this case, you're looking for a shale that fits the Barnett model. And if it does, then great, this shale's going to work. But if it doesn't fit that model, then they were often, they were walked away from. And I felt like this was a very limiting strategy to take when exploring for these different shales, because certainly there are aspects of all these shales, some fundamentals that they all have in common. For the most part, they have organic material. They do best with, horizontal drilling, slick water, hydraulic fracturing, those types of things. But when you really start digging down into these shale plays, I find anyways that they're often more different than they are alike. And so what we should really be doing is concentrating on the methods of how we evaluate these shale plays, and not looking for an answer that we found somewhere and applying that elsewhere. And I thought that whole concept is brought together when you look at these two incredibly prolific shale plays in the Appalachian Basin, and realize just how different these plays actually seem to be. And so that's what I'd like to do. I want to talk about some of the commonalities of these things, but then go through inorganic geochemistry, some sedimentology, and discuss it, and then we'll wrap it up with some other thoughts I have here. But you know, we're talking about things that they have in common. Both the Point Pleasant and the Marcellus, the organic matter is the primary site of hydrocarbon-filled porosity. And so the above SEM image there is organic matter pores hosted by organic materials in the Point Pleasant. The lower is the same for the Marcellus. And if you look at these cross plots, we can see that there's a very strong correlation between organic carbon and gas-filled porosity in these two units. So the production mechanism is largely the same between these two plays, but I think that's about where the commonalities of these two plays ends. So when we start looking at basin chemistry, one of the things I look at, and I apologize, this is a very boring slide, just a bunch of words on it, but one of the things I start looking at is the oxygenation conditions under which these rocks accumulate. And the reason for that is there's many different ways to preserve organic material, but one of the most successful ways is for that organic material to accumulate under oxygen deprived conditions, because then you lose less organic material to oxidation. There's less critters living there that would filter and feed and consume that organic material. So the less oxygen you have, the higher the preservation potential. So it's a first principle area that I like to start. And one of the things you can look at is iron enrichment. Now, the average shale value, you just go out anywhere, survey a bunch of shales, you're going to get a ratio of about 0.55 of iron to aluminum. When it starts going above that significantly, generally what you're seeing is reactive iron being sequestered in that sediment as pyrite. And that happens under oxygen depleted conditions. So anoxic to eusinic, which eusinic just means there's free hydrogen sulfide in the water there. So that's where you start seeing that happen. You'll also, because of that too, you'll often see that iron and aluminum are decoupled from each other. So you're not seeing iron that's just being brought in with the clastic influx, but you're seeing it being pulled out of the water, out of surrounding sediments in order to form this iron. There are instances, though, and you see this with a lot of these geochemical parameters and many parameters, and it's why I try and take a holistic approach, and it's also why I cover so many different aspects in one talk, is that they aren't perfect indicators. So you can have conditions where sediments are accumulating under an anoxic environment, but you have very high sedimentation rates. This happens in the Black Sea, where you have tributaries coming into the Black Sea. It's anoxic, but you have a very high clastic influx, and that can swamp that reactive iron with less reactive detrital iron. So you'll actually see a lower iron to aluminum ratio that might indicate more oxygenated conditions, even though it's accumulating under eusinic conditions. So you also need to take, sedimentation rates into account. Now, when we look at the Point Pleasant, what we can see is that in general, that range is about 0.42 to 0.45. So we're seeing we're at into slightly below the iron to aluminum ratios of the average shale. So this is suggestive of oxygenated to disoxic conditions under which the Point Pleasant is accumulating. When we look at the Marcellus, on the other hand, the iron to aluminum ratios are often much higher, from about average shale values up to as high as 0.76. Now, this implies that we're more on the anoxic eusinic side of things in the Marcellus. So right off the bat, we're starting to see that there's a difference in the chemistry under which these things accumulate, and it's telling a couple different stories. Now, we do have a number of iron to aluminum ratios that are lower than would be expected, and we think what we're seeing here is that swamping there, because we do know, as far as black shales are concerned, the Marcellus accumulated quite rapidly. And just to sort of pin that down for you, the Barnett and the Marcellus span about the same thickness range, from, nothing but like where we kind of play it around 50 feet thick up to, 300 feet, 350 feet thick. The Marcellus accumulated in about 1.1 to 1.5 million years. The Barnett, on the other hand, is somewhere around 25 million years. So just to give you an idea of the differences in the sedimentation rates there between those two deposits. So the fact that we're seeing some swamping in that iron to aluminum signal isn't a surprise when we consider those sedimentation rates. We can also look at uranium and molybdenum enrichment profiles. And the interesting thing about these is they both accumulate under anoxic conditions. However, they accumulate under different mechanisms, whereas uranium is largely controlled by the presence of organic material, and it attaches that organic material across a sediment water interface, and therefore sedimentation rates and organic richness play a large role in its accumulation. Molybdenum can get into there. It can be attached to organic material. It can be held in metals, and it can be enhanced through particle shuttle mechanisms. So what we can see is variations as you move from left to right across the slide in those profiles are indicative of different degrees of basin water restriction. So if we see, as the enrichments are increasing, if we preferentially see more uranium and less molybdenum attaching, that's generally a restricted basin where you're drawing molybdenum out of this reservoir faster than you are uranium. So you see the enrichment of molybdenum relative to uranium going down through time. When you see the opposite of that, where molybdenum is increasing relative to uranium as these enrichments increase, that's very typical of what you would find in a very weakly restricted environment, like an open marine, maybe like an upwelling environment sort of a thing, where you have constant connectivity to that reservoir of molybdenum and therefore can keep supplying it to that system. The other thing that we commonly see under usinic conditions are what we see in the third diagram there, where we see ratios that run parallel to seawater concentrations, yet they're anywhere from 1 to 5 times higher than those seawater concentrations. And this requires intermittently sulfidic bottom waters and intermittent reconnection to the global ocean and resupplying that molybdenum. So what happens here is molybdenum attaches to these particles, they sink through the oxygenated part of the water column, they hit that sulfide chemocline, it dumps the molybdenum, and those particles eventually reform and grab more molybdenum out of the oxygenated part of the water column. And when you do this, you can begin to attach a tremendous amount of molybdenum to these samples. But again, it requires intermittent sulfidic conditions. It requires a fluctuating chemocline. That boundary between the sulfide bearing water and the oxygen bearing water needs to be moving around, and connection to that global ocean there. So it implies a very dynamic system. So if we look at the Point Pleasant, and just back when we were looking at those diagrams, just note that they go from 1 to 1,000 and on the molybdenum scale, and about 1 to 100 on the uranium scale. The only way that we can get, and that's taken up by these, that's marked there by that red dashed line. The only way we can even get any of these samples to show up for the Point Pleasant is we got to take that scale down to 0.1 instead of 1. So we barely have any molybdenum in uranium in the Point Pleasant that's above the levels of detection. And if we make these plots that we're used to seeing at the scales we're used to seeing, none of this data would even show up on such a plot there. So again, that is suggestive of an oxic to disoxic waters under which the Utica Point Pleasant is accumulating there. So we see no evidence in the molybdenum and uranium enrichment of bottom water anoxia. The Marcellus, on the other hand, we see data that is parallel to the seawater concentrations and often enriched there 3 to 4 times what that seawater concentration is. This is indicative of that particle shuttle mechanism that's occurring in the Marcellus. So we have a scenario where we have fluctuating redox conditions. And we have intermittent global connection back, connection back to that global ocean that's resupplying that molybdenum budget through time there. So again, a very, very different, different mechanism during deposition of the Marcellus than what we see during the Point Pleasant. Now, the next thing I want to move is away from the geochemistry a bit and talk a little bit about pyrite morphology and specifically framboidal pyrite. And the reason that I'm interested in this and have been for some time is that they can tell you a lot about where that chemocline is in the water column or in the sediment. So framboids, they're just these spherical aggregates of pyrite crystallites. They start off as monosulfides, and particularly greigite, which has magnetic properties, and that's what pulls these crystallites together into these spheres. The interesting thing about them is that this process of going from these disordered monosulfides to ordered monosulfides to pyrite, that occurs right at the sulfide chemocline because they need oxygen as a reactant in order to make some of those early phases of those iron monosulfides. So these framboids are forming right where that chemocline is. And that's really helpful because if that chemocline is up in the water column, which you can see on the left side of the diagram there on the right, these framboids can only grow so large before they become too heavy to be supported by the water column and they sink away from that chemocline and they stop growing. So if you have a chemocline that's up in the water column, generally the framboid population is small, around 5 microns, and very well sorted, a standard deviation of less than a couple microns. If that chemocline is at or below the sediment water interface, and these framboids are forming in anoxic pore waters, then the only controls on their size become space to grow and an availability of reactants. So you see much larger framboids and you see a much higher diversity of size of these framboids. So we can use that to get a relative understanding of if that chemocline's up in the water column or if it's in the sediment water interface. The other form of pyrite that we find is euhedral pyrite in these systems. And the interesting thing about the euhedral grains is that they form from the direct reaction of hydrogen sulfide and iron. They don't need to be near the chemocline. So these things can form away from that sulfide chemocline and, in deeper and anoxic pore waters and with less reactive iron. So they can tell you that you have anoxic pore waters, but they're telling you that if that's forming, the chemocline probably isn't anywhere nearby. And then this was published by Wignall, this table down here at the bottom, but you can use this then to sort of gauge the degree of bottom water oxygenation of the basin. So if you have no framboids and rare pyrite, then it's probably oxic. And as you start seeing more euhedral grains, it's indicating that the oxygen levels are falling, and then you start seeing framboids. Again, it's getting you more into that lower disoxic to anoxic, and then as those framboids start getting really, really small, it can tell you that you have these, eusinic conditions or these persistently sulfidic bottom waters there. So that's the model that we're looking at here in order to track where this chemocline is. Again, not clear cut, not cut and dry. And so we first want to look at the Point Pleasant. So again, if you recall the elemental data, what we generally see is it's indicating a oxygenated system here. The pyrite data, and you see that on the table on the left, that red box, if we look at analyze the SEM images, about 0.5% of that image is pyrite. And of that pyrite, only about 20% of it is framboidal pyrite. So not a whole lot of pyrite, not much of it is framboidal. But the interesting thing is if you look at the other table and then the summary down below, the framboids that are there are very, very small, and they're very, very well sorted. So they average just under, just over 4.5 microns, under 5 microns. And the size range, the standard deviation is less than 2 microns on these things. It's exactly what you would expect to find under persistently sulfidic conditions. So if you were to go to the Black Sea, for example, and pull sediment there or even out of the water column, this is exactly what you would find. But again, the other thing that doesn't really comport with that is there's hardly any. If you look at the framboids per square millimeter, and we did that by just counting the number of framboids in these SEM images, we had the computer do it, there's not very many in there, and that'll make more sense when we look at the Marcellus data. There are larger framboids in there, greater than 10 microns, but they're pretty rare, you know, only about 2% of the population or so. So we have a bit of an issue here that needs to be explained, because all the data I've talked about beforehand, from the geochemistry to the amount of pyrite in the system, says that this is an oxygenated to disoxic system. But if we look at all the framboidal data, this is saying this is an anoxic to eusinic condition here, and we need to reconcile that. And that's all this slide is saying here. The framboids are saying that we're in this story where that chemocline's up in the water column. Everything else is saying that we're in the story where we're dealing with an oxic to maybe disoxic at time water column here. And I think the answer to this is a lack of reactants in the system. And this was noted in the Santa Barbara Basin, where you can go out there and, like, going back through the last, I don't know, like 40 or 50 years, they have measurements of the actual oxygen content of the water, of the bottom water in the Santa Barbara Basin. But the framboids, they're only about 4 microns in diameter. But what happens is you have all these felsic terrains that surround that basin feeding sediment into there. So it's a very iron limited system coming into the Santa Barbara Basin. These framboids have a tendency to nucleate at multiple different areas. So they kind of nucleate at the same time all over. They exhaust the supply of iron and they stop growing. And I think something similar is happening in the Point Pleasant. If you look at these iron to aluminum ratios, we're depleted relative to the average shale in the Point Pleasant. So it says that the supply of reactive iron that's coming into the basin is limited. And indeed, if we start looking at, like, the number of framboids per sample, and we compare that to aluminum, which is a good proxy for classic influx, what we find is that the more sediment coming into the basin, and therefore the more reactive iron coming into the basin, the more framboids we see. So it's a pretty clear indication that the delivery of iron to this basin is a controlling factor on these framboids. So they're likely nucleating at many discrete sites, exhausting that supply of iron around them, and then their growth is then arrested, and it happens that growth is right around 4.5 microns there. So that's sort of the story with the Point Pleasant. And again, let's contrast this now with the Marcellus, where if we look at the percentage of the SEM image that is pyrite, it's almost 2.5%. So it's almost 5 times what we saw in the Point Pleasant. And of that, half that, so more than double the pyrite, occurs as framboidal pyrite. Moreover, the framboids in general are quite small, less than 6 microns, but we do find large framboids over 10 microns in diameter in almost all samples. So we have a mix. We have a dominant set of framboids that are very small, but we do have a subset of this larger cohort. And if we look at the image there in the bottom right, we can see this sort of spans eusinic to anoxic and disoxic there, depending, especially if we're looking at just, you know, the Marcellus data. The Geneseo's a bit more in the disoxic to anoxic world there, but we seem to see a fluctuation between anoxic and eusinic conditions here. So what this is telling us is that we have a very dynamic system in the Marcellus, where most of the time it would appear that the Marcellus is accumulating under an anoxic or eusinic water column, where that chemocline is up in the water column, such that the majority of those framboids that are growing in the water column and sinking away their growth to the rest, and you get these small framboids. But the large framboids have to be accounted for. And what's probably happening is that there are times where that chemocline is forced down to or below the sediment water interface, and that's where these larger framboids grow. And you can see that just in that image on there. We have large diagenetic framboids occurring alongside small syngenetic framboids and framboids that have been welded where you have secondary growth of pyrite and euhedral grains. So again, this model is very consistent with what the uranium and molybdenum profiles were telling us, that you had to have a fluctuating chemocline and you had to have connectivity to that global ocean. We're seeing that borne out here in the framboid data as well. So that's a nice consistent story there. The last thing to hit on here, which is to look at, let's look at the quartz in the system. So we have two different types of quartz that can come in, extrabasinal and intrabasinal. So quartz that's derived from outside the basin, the detrital input, and quartz that's derived from inside the basin, which is things like radiolarians, diatoms, those sorts of things that, or not diatoms, but forams. And so these things, they fall, they undergo a dissolution process and a reprecipitation through multiple steps of those processes, and ultimately they form what becomes often referred to as biogenic quartz in the system here. What we see commonly in the Marcellus is that source of that quartz is from radiolarians. Millie Wright was one of the first to publish on how you can detect that, and you can compare it to zirconium. So the only way zirconium gets into the basin is through riverine transport, so through that clastic delivery by river system. So if your silica correlates with zirconium, that's a good indication that it's detrital silica. But in that upper left-hand diagram there, you can see what they have labeled as a biogenic trend there. And this is quartz that is decoupled from that clastic influx here. And this is an indication that you likely have some other source of quartz other than clastic input there, and it's likely biogenic in nature. So if we look at the Point Pleasant, you can see this cross section. It goes from eastern Ohio into northern West Virginia and up into southwestern Pennsylvania. In eastern Ohio, we don't see any evidence of biogenic quartz at all. In West Virginia, we still don't seem to really see anything definitive. The zirconium and the silicon still seem to correlate with each other here. But then when we move into southwestern PA, we see a very, very strong trend in biogenic quartz here. So this suggests that whatever is driving that influx of biogenic quartz into the Point Pleasant is not ubiquitous across the Point Pleasant basin, but it seems to be much more localized. The Marcellus, on the other hand, no matter where we look, and this is a pretty narrow cross section from northern West Virginia up into southwestern PA, but I've done these studies in New York and in northeastern PA, in central PA, Ohio. No matter where you look, you can always find evidence of biogenic quartz in the Marcellus. So this production of radiolarians and their ultimate contribution to that quartz that we find in the Marcellus seems to be much more ubiquitous. So all of that boils down to this story of let's look at these things. So they're both an organic rich or an organic enriched shale, where the dominant reservoir for us is organic matter hosted pores. But it would seem that is, for the most part, where their commonalities end. If we look at iron availability, we had excess iron in the Marcellus. We were limited in the Point Pleasant. We're depleted in uranium and molybdenum in the Point Pleasant. We're enriched in it in the Marcellus. The quartz, the framboids, again, same story. They're different. And ultimately, we can conclude that the Point Pleasant accumulated under disoxic conditions, or maybe even oxygenated conditions, while the Marcellus accumulated under anoxic to euthentic conditions, which is really interesting because this is a plot from IBEC in 1982, and what you have are these two different black shale trends. So one says, black shale A, you preserve organic material by rapidly burying it. And this generally happens in areas where you have organic material accumulating under an oxygenated water column. Because the only way to keep it from being consumed by benthos and burrowing critters and oxygen is to rapidly remove it from where they can access it, get it buried, and push down into anoxic pore waters. The other side of that is this black shale B trend, which is the opposite. As sedimentation rate goes down, TOC is going up. And what we're seeing here is we have a system where basically we can say that organic matter production, for all intents and purposes, is constant and preservation is constant, and therefore the amount of organic material per unit of rock is a function of dilution by clastic influx. So this is the opposite. The higher the sedimentation rate, the lower the TOC that we see. And so we can see that in the cases of the Utica and the Marcellus, they accumulated under quite opposite conditions, which has I think has bearing, maybe not so much in the development phase, but certainly if you're using a Barnett or a Marcellus model in order to go and explore. So like, let's say we figured out the Marcellus first, and now we're gonna go, okay, where do we lease the Utica Point Pleasant? If you use the Marcellus model, you would be looking in the exact opposite area that you should be. You'd be paying $5,000 an acre for the worst acreage for the Point Pleasant, because the Marcellus, you want low sedimentation rates, high TOC, but the only way you're going to preserve the organic material in the Point Pleasant is if you're in an area that has high sedimentation rates. And we see that borne out in the Point Pleasant. So this is a busy slide, but what's interesting is the Point Pleasant has a number of these shell beds in here. So we have mudstones that are largely devoid of shell material, and then you get these shell beds in there, and then you're back in the mudstones again. And what we find is that there's largely an inverse correlation between TOC and the mudstones and the occurrence of these shell beds. And what's happening here is that the organic material is accumulating under rapid conditions. So these shell beds, which are organic pore, are largely in situ. They grow in situ, and you see some like tempestite reworking of these types of things. But these are the time-rich intervals, and then they generally get killed by what they call abruption or suffocation layers. And these are these organic-rich turbiditic type deposits that are coming in, bringing organic material down with them. They suffocate these hard grounds and these beds where these shells are growing, and then the cycle repeats itself all throughout there. So we see evidence even at the core scale as well that the high sedimentation rates in the Point Pleasant is where the organic material is. The Marcellus, it's the opposite. If we take the organic material we have, and I went through this whole process of using the original hydrogen index of this material and back calculating what the original TOC was for the Marcellus. So basically you're eliminating the overprint of thermal maturity. What we find is that the highest TOC rock corresponds to the lowest clay volumes here. And that's depicted in cross plot on the log scale, and it's depicted in map form at the spatial scale here. So you can see these big lobes of clay that are coming out into the basin. And where you're in the more proximal settings, we have a lower TOC than where we're in the more distal settings out here. So again, very, very opposite ideas here. And so what this brought me to, the last thing that I wanted to touch on was this idea of what I personally needed to do is something that I found often in the literature, which I call like in vogueism, in my attempt to avoid it. Because if you look at the research volume, which I'm sure many of you have, on organic rich mudstones, you seem to find like there's a time period where this was the model. It seemed to start off with the Black Sea. It's, one of the most close approximation to some of these, Paleozoic Epiric seas and Mesozoic Epiric seas that we're used to. And that was sort of like the model, this idea of this very, very deep water, greater than 1,000 meters, stratified basins. And then in the 80s, like this idea of upwelling came in. And then now suddenly it seems like all these Paleozoic shales and Mesozoic shales are all the result of upwelling. And then it went to anoxia and eugenic conditions. Now lately, there's people who are the opinion that these things were never anoxic, they were never eugenic, they accumulate under oxygenated conditions. And now we're even starting to see that take form with water depths as well, where, you know, you could be walking out into like knee-deep water and you're in these, you know, black muds of the Marcellus and things like that. So there seems to be an in vogue idea that sort of dominates it, you know, for a certain period of time until something else comes along. And I wanted to avoid that. And I wanted to give an example of that. So if we look at upwelling, there's a paper that came out in the early 1980s. And if you look at what they came out with you know, sources that are explainable by upwelling based on their model, they're suggesting that 75% of the black shales that accumulated during the Devonian were the result of upwelling. So again, we're talking the Marcellus, the Geneseo, the Rhine Street, Dunkirk, and it goes on and on and on. I mean, the Devonian, especially in North America, was a great time for black shale deposition. And it's saying that the majority of these likely accumulated under an upwelling environment. And, you know, it's a reasonable assumption. So if you look at like modern day, where coastal upwelling occurs, it occurs on the eastern side of ocean basins where the winds blow towards the equator and parallel to the coastline. So you have these, you know, gyres, ocean gyres that are working out there, and where those currents come down, you know, towards the equator, that's where you see upwelling. So what's happening is the wind is blowing down along the coast there. The Coriolis effect induces Ekman transport that is perpendicular to that. So it moves water out to sea, and therefore it has to be replaced by deep water, which gets upwelled. And that's what brings you all your nutrients and all that stuff, and can stimulate high productivity and make you need a wetsuit even though you're in California, and surfing and all those sorts of things there. So it's a great model for the accumulation of organic rich shales. When we look at the middle and upper Devonian shales, it's an incredibly appealing idea, because if we look at the basin, at the time we were about 30 degrees south latitude moving towards the equator through time. And so we have these winds then that would be blowing up the side of this basin here, Ekman transport out into the basin. It's exactly what you would expect to find for an upwelling environment. But one interesting thing to note about modern day upwelling is that it's largely controlled by the strength of winds. And when those wind speeds die down, that's when you start to see upwelling shut down. And what we often find too is that as we move into summer months and we start losing that like pole to equator temperature contrast, and when we have El Nino events, upwelling largely gets shut down off the west coast of the United States because things are too warm for that mechanism to work. So if we go back to our Devonian model, you know, the PCO2 levels were estimated to be about 13 times what they are today. It's, you know, argued it was probably a lethal environment on land. This would greatly reduce that polar to equatorial temperature gradients. It would reduce wind speeds and likely reduce, you know, the plausibility of upwelling occurring down here. And what would you expect though if it was? Well, then you would expect the highest TOC deposits would occur along that paleo shoreline there. So you would expect to find them in the eastern part of the basin, the present day coordinates. Also, we would expect molybdenum and uranium profiles that are indicative of an open marine system in an upwelling environment. And we don't see any of that occurring at all. So again, we see the exact opposite of that, where the most organic rich deposits are in the distal outboard section of the basin, not where we would expect to be seeing upwelling. So although it's a tempting model, and it was popular at the time, when we get down into the nuts and bolts of it, it just doesn't seem to work for the Marcellus in this case there. So, but when I say that, you know, avoiding this, I'm not trying to suggest that these processes never occurred. Another thing that I see is commonly, and I've been guilty of this early on in my career myself, is that it's one model must have been occurring throughout, that entire basin in both space and time. So the Marcellus was anoxic. It was anoxic from beginning to end, and it was anoxic from West Virginia to New York. And we see evidence as we get down into the nuts and bolts of this that's not the same. We can find areas where we had higher sedimentation rates, lower sedimentation rates. We can find influxes of oxygenated water into these systems. They're incredibly dynamic, and it is very, very difficult to say that one model was acting throughout geologic history, throughout a basin, throughout even any one particular shale, throughout its depositional history in space and time. So I guess the ultimately is like, this is where I came to this idea that, the data needs to dictate the model, and not let myself get caught where where now that I have a model that works, trying to force that onto another shale play. And my last slide here is I understand why it happens. Neil deGrasse Tyson said everybody wants nice and tidy answers. And I would say that in this case, you can insert everybody with management. But nice and tidy, it just doesn't exist. We operate in gray areas here. And largely as geologists, I feel like we're operating at the boundary between the known and the unknown. And saying all that, again, this is an excellent paper on the Marcellus Shale that's from a core, and this was, again, the type eusinic deposit. So this goes through all of the geochemistry and everything that you would expect to see coming from a eusinic deposit in the Utica Creek Formation. And everything about it is accurate, but you can go to the type section of the Utica Creek on Utica Creek, New York, go down to the bridge, dig around in there, and you will find this incredibly fossiliferous gray shale, which is called the Hallahan Hill Bed, which is one of the first incursions of Hamilton fauna into this basin at the time. So indeed, the Utica Creek is a type eusinic deposit, but we also have to account for the fact that it's incredibly dynamic and supported one of the most robust ecosystems in oxygenated waters early on in its depositional sequence. And with that, I will conclude the talk, and I think it leaves us 10 minutes or so for questions.
Excellent. Well, thank you, Randy, very much. Absolutely fascinating material you covered, and you kept within good time, which is rare for one of our talks. So we do have some time. There was one question. Wallace asked, "Can you make these measurements?" And I believe he was referring to some of the core measurements you were covering earlier, also with well cutting samples. And there was an answer here. Somebody thought that both would work, and I wanted to see if you had any thoughts on that as well.
Yeah, absolutely. So you can core cuttings, hand samples, any of that stuff works for this type of analytical work. With cuttings, what you need to be cognizant of is the preparation procedure and extensive cleaning of the samples, especially depending on what elements you're trying to look at. So for example, if you have high productivity waters, you get a lot of barium is associated with high productivity, but it's conservative under anoxic conditions, so it doesn't come out of the water. But if you have barium accumulating in the water, and then you flip over to oxygenated conditions, you'll dump a lot of that barite, and you'll get barite nodules that'll occur. So right below the Cherry Valley is a zone loaded with barite nodules, and that's right where you're coming up into these regressive systems tracts deposits out of this anoxic material, and you're moving into more oxygenated conditions. You get all this barite in there. If you're interested in that, if you're using say that's your target zone, and you're going to use barium to understand that, or just to understand those dynamics. The problem then is I'm sure you know where I'm leading with this, is you got to be really careful, because we're also using barite as an additive to the drilling mud. And if you don't effectively clean those cuttings, you're going to get, that barium contamination in your signal. The other thing is that the signal with vanadium, for example, overlaps with barium. So if you have a whole lot of vanadium or if you have a whole lot of barium, an XRF can have a difficult time parsing out which one is which there. So that can also be an issue if you have a lot of barite in there. So you can use cuttings, but you just have to make sure that they are thoroughly clean, either by yourself or by a lab that's aware of that in order to use it.
Another question Ron was asking, he can elaborate if you'd like. How do phosphate concentrations differ between the Point Pleasant and the Marcellus? The 80 million year difference in age saw the diversification of fish. So would that be influencing the phosphate concentration too?
Yeah, so they're very low. We don't. So one, phosphorus that's a difficult element to detect using XRF, especially energy dispersive XRF technologies, which is most commonly what's used. You use wave dispersive, but that gets more expensive and time consuming to use that. So it's a difficult element to detect to begin with. And what we see is that we have, for the most part, low abundances of it in these units. But when we do find it, especially in the upper Devonian, it is often associated with lag deposits or sediment starvation surfaces, and very often those nodules are sited on things like fish bones and teeth and those sorts of things. You can kind of crack some of these open, and find that material. And as a matter of fact, Scott McHale and I were out at Sturgeon Point just the other day, last week. We actually found a bit of fish bone that was incorporated into a phosphatic nodule. But it's relatively discrete, throughout there. Like, you find these nodules at discrete intervals. It's not distributed evenly throughout the system there. But yeah, to your point, Ron, I would expect that to definitely play a role in the overall abundances of phosphate. But we still don't see a whole lot in these shales.
Ron, would you like to just elaborate on that?
Well, not really. I think you did a good job answering the question for me. I did actually have another question that I typed, and it kind of jumped in with my previous question. I was wondering if you could use any of the other oxyanions to maybe fine-tune some of the geochemical sensitivity. Arsenic, selenium, vanadium, kind of behave geochemically like uranium and molybdenum.
Yeah, absolutely. So, the interesting thing is that these different elements, they'll come out under different types of reducing conditions. So like vanadium, that generally precipitates out under denitrifying conditions. Whereas the molybdenum comes out, you have to have these euthynic conditions in order to get that. So if you have, a lot of vanadium, but not as much molybdenum in there, that can give you an idea to what's going on in terms of, what's being used as an oxidizing agent for that organic material. When you start getting to answer the other elements, yes, but you need to be using a technology that can accurately measure them. So again, with portables, like handhelds, like what I got sitting next to me on my desk there, you need a lot of that stuff to get accurate readings in it. And so they become less useful if you have lower abundance of. But if you start moving to things like, different forms of ICP data or wave dispersive, then yeah, those would become much more handy. And it's funny that you mentioned arsenic too, because one of the ways that we're identifying burn down, which is you have organic, black shale that accumulates under anoxic conditions, which is then overlain by oxygenated conditions, and that oxygen front will start moving down through the sediment and remobilizing these metals that were deposited under anoxic conditions, and they can then concentrate them in much narrower bands. And one of the ways that we identify that is by what we found in the Rhine Street was by looking at the arsenic levels. So we go from anywhere from about like 5 to 10 parts per million in the continuous black shale of the Rhine Street. And then when you get into these beds that have suffered burn down, those arsenic levels shoot up to like over 100 parts per million arsenic. And that's because you took arsenic that was in this much sediment, and now you concentrated it all in this much sediment down there. So yeah, we do use a lot of these different proxies. Nickel's another one. There in some instances that I think that I want to say it's the Eagleford or maybe the Niobrara, I can't remember which, but there's some companies that have actually come up with a statistically valid way of just calculating TOC based on empirical relationships to nickel. It's that tight.
So a couple more questions just coming in now, actually a few more. Do you know if zirconium silicon ratios have been useful for understanding depositional history in the Eagleford?
I haven't. I don't know if it's been applied in there or not. But it'd be a very easy test to do if you could get your hands on some of that data. If you had that elemental data, you know, you could set up those cross plots and look and see what's going on there. Yeah, but I don't know. I was actually just earlier this year, I was in Texas, South Texas, collecting a bunch of Eagleford for a client along those outcrops along Route 90 down there. And I don't know if they intend to do any of that type of work with it or not, but it'd be interesting to find out.
Another question, did you find any associated siderite in these systems? And what is the role of carbon dioxide, if present, in sequestering iron?
So where we generally see siderite is in many of these shales have many of these shales host carbonate concretions in them, and within those are what they call like septaria or septarian cracks. And what we find in there is the initial precipitation of an iron poor calcite. And what's happening is all that iron's going into pyrite production at that time. But then if the sulfide ends up being consumed, and there's still reactive iron, what you'll then start to see is the formation of siderite there. That iron will start forming siderite in those cracks. And then eventually that will be, that'll end up being followed by barite in there. So that's about as common as I see it. Like when you move around, like in some of these marine zones and like the Conemaugh and the Pennsylvania up here, like we see siderite nodules like all over the place. But I haven't seen any significant occurrence of siderite in these rocks beyond what you would find occasionally in these septaria. And what was the other part of that? Carbon dioxide. So I think what we get, so one of the things where I know that plays a role to some degree is we end up seeing a decrease in the pH of these bottom waters when they get anoxic, and some of that's owing to the increased carbon dioxide in there. And some of the evidence for that is when we look at these lag deposits that we find in the black shales. So what happens is you have that chemocline often occurs at a boundary that's also generally a density contrast as well. And anytime you have a difference in fluid densities, the most obvious to us is the difference between ocean water and the atmosphere. You get wave action along that. Well, that can happen at these pycnoclines that occur along with that transition from anoxic water to oxygenated water. And you get what they call internal waves. So these are waves moving within the water column as opposed to like at the top of it. And where that impinges on the sea floor, it'll erode. And what we find is that it dissolves the carbonate allichem. So if there are concretions, they get corroded. Shells, anything like that gets dissolved. And what you end up with is these like placer deposits of pyrite and phosphate and, you know, quartz grains, other you know, indissolvable, unsoluble material that we find in there. And some of that's owing to these changes in the pH, which are associated with that carbon dioxide that's, you know, then associated with these anoxic waters. So
Looks like one question. Jeff, I don't know if you'd like to ask your question, if you're able to unmute yourself. I'm not sure if it was fully answered, so I'll let you kind of take the stage.
Yeah, hey Randy.
Yes.
I typed my question in, I guess about the same time that Justin was typing. But my question is, a massive and regional volcanism is one idea for the end Devonian extinction. So I was asking again about volcanism during the Devonian for lots of things that it could be effective, like radiolarian productivity. You've already talked a little about zircon silicon ratios, iron influx from different magmatic areas. So I was just wondering, have you looked into that, how that affected things like iron productivity and so forth?
Yeah, so it's really interesting that you bring that up because exactly. So at the base of the Dunkirk is the Franium-Fumenium boundary for those that are not familiar with it, which is one of the big 5 mass extinctions. And there has been volcanism, extraterrestrial, impact. Any of that stuff has been offered as a cause of that. The interesting thing was that in Germany, at the equivalent sections, there's a bentonite, or a Nash bed anyways, that's just below this boundary, and it's dated at I think 773 million years, something like that. But it gives a really precise date for the Franium-Fumenium boundary of about 372 million years. The interesting thing about that is they've been unable, using that precise date, they've been unable to link that to an impact or necessarily to volcanism that they can say that this is a smoking gun. And the other part of that too is that extinction event actually started much earlier, about 5 million years earlier, at the Pipe Creek in our area, which is also called the Lower Kellwasser bed, and then culminated up there. So it seemed to occur in 2 pulses as well there. So I know, so all that, my other part of that is that generally what I have found is that when we look at extinction events, like even if we look at the end dinosaur extinction with the impact, there's impacts of that scale and size that you see no perturbation in the fossil record of at all. There's the end Permian has been blamed on, I think, like eruption of traps, maybe in like the Karoo Basin or something like that, but large, huge, massive volcanic eruptions. Same thing, you see stuff of that size and scale elsewhere. No evidence that it really caused a mass extinction in the fossil record. And what you do seem to find, though, is often there's an argument over it was this, no, it was this, no, it was that, and all these things kind of occur around the same time. And what I strongly suspect is that these things are acting in concert. You have things that are stressing these systems to some breaking point, and then it just takes something that they would normally survive, even albeit a large meteorite impact, or like the eruption of the Deacon Traps or something like that, and that's enough to hit this tipping point where these ecosystems collapse. And I think the end Devonian right now, because of the fact that there isn't a precise volcanic eruption event or impact event that we can tie to that 372, I think the idea is to blame it on global anoxia, because you do see this stuff rising up into these shallow seas. You see reef communities are really getting hammered. Stromatoporoids are getting hammered at this time. And that seems to be the smoking gun, but I would not be surprised, though, if you're dealing with conditions that are already stressed because of some of these other processes, like you said, the volcanism and whatnot that's occurring there. And so some of that, I don't think I directly answered your question other than to point that out. And I will say too, I know in the Maori, someone's going to be talking about that, I think, at your next meeting. That was originally all of the quartz in the Maori was assigned to volcanism, but there's a big mass balance problem with that there's not enough volcanism to account for all the silica in the Maori. And what that's largely been demonstrated to be coming from is also radiolarians there. So that's also a good biogenic quartz system there as well. So so Jeff, I don't know that I completely answered your question, but at least you kind of know where my mindset is with it.
Okay, thanks.